will be two talks in the afternoon sessions. The first one will be given by Professor Lee, who will continue his report on the exact results on supersymmetry theories. So welcome him.
Thank you. First of all, I'm not a professor. Anyway, let me just start this afternoon talk. It's more like a research seminar. So before that, let me just go through what we discussed in the morning. So we discussed about the supersymmetry algebra given by a T2/1, and reconstruct some supersymmetry Lagrangian and the truth there. Then compute the partition function of this two-dimensional supersymmetric theory using this localization technique, which is given by these expressions for the gauge linear sigma models. And we also discuss about this regularization scheme dependence on the finite term of the sphere partition functions as well. And so this, and we also discussed about the exact two-sphere partition function of the lambda Ginsburg theory. And using this new exact result, we investigated this mirror symmetry from these two-sphere partition functions. We saw that these two-sphere partition function of these two theories, which are mirrored to each other, exactly agrees to each other. And finally, we discussed about this, we investigated the space of the gauge linear sigma model from this two-sphere partition function result. Okay, so
just to make sure I understand. When you say the two-sphere partition function agree between the two theories that are mirrored, you are ignoring the dependence of the partition function on the other parameter on the.
Of course, it's only on the Kähler parameter.
Say up to.
But yeah, there's one more comment. So if I insert, if I define the supersymmetric theory on two-sphere preserving other NTU-1, where U1 is identified as axial U1 R symmetry, then this two-sphere partition function depends on complex parameters. And then when you compute this two-sphere partition function for that supersymmetric theory, you still get the agreement for the complex parameters in the superpotential. So, yeah. Any other question before I start? All right, so there's another. So let me discuss about this other applications of these two-sphere partition functions, which is the Walsh instanton correction, or computation of this Walsh instanton correction to this jamological matrix, which is also known as the Gromov-Witten invariant computation. So let me first remind you these basic things about the string compactification again. So we have a type 2A string theory and compactifying the Calabi-Yau manifold. There are some Kähler and the complex structural moduli space. And this moduli space will define the space of the marginal couplings of the corresponding 2D and equal 2 superconformal cell theories. And for many purposes, it's very important to know the exact jamological metric on this space of the marginal couplings. But this jamological metric receives various quantum corrections, including this Walsh instanton corrections. As I told you earlier in this morning talk, this mirror symmetry has been providing a good solution to these problems, computing this Walsh instanton correction exactly. But the only problem is that there are larger class of Calabi-Yau manifolds where we cannot find the mirror description systematically. And because of that, people would like to find some more direct and powerful method to compute this Walsh instanton corrections without relying on this mirror symmetry. And this is what I want to discuss from now. And we also would like to put some D-branes and orientable plane in this Calabi-Yau manifold and want to study their physics from the string theory point of view, also from this Walsh point of view. In this case, we need to study this boundary state and the cross-gate state in the two-dimensional theories. Okay, so as I emphasize again and again and again, these exact two-sphere partition functions can provide a direct and powerful method to compute these non-totality corrections to this jamological matrix without use of this mirror symmetry. More precisely, by computing these two-sphere partition functions with certain supersymmetric theory in 2 dimensions, which can describe a given Calabi-Yau space, one can immediately read up this e to the minus k, where k is the exact Kähler potential on the Kähler moduli space of this Calabi-Yau manifold. In other words, from these quantities, you can compute the jamological metric by taking second derivative of it. the scalar potential is exact in alpha prime corrections. And once you know these exact scalar potentials, you can also compute the so-called Gromov-Witten invariant of the given Calabi-Yau manifold. It is also interesting to note that the scalar potential, by definition, is ambiguous under the scalar transformations, which is also consistent to our previous discussion in the morning that, this finite term of the two-step partition functions also ambiguous of the scalar transformations. So this formula somehow seems to make sense in that sense. So this formula was first conjectured by Jokers, Kumar, Lapan, Morrison, and Boma after working on many examples known in the literature. And finally, they also predicted some new results regarding this Gromov-Witten invariant of certain Calabi-Yau manifold whose mirror description is unknown. So let me first consider some simplest example of that, which is the famous quintic threefold. The gauge linear sigma model, which flows to the nonlinear sigma model on this quintic threefold, can be described by this two-dimensional supersymmetric gauge theory. The gauge group is U1, and this gauge theory is coupled to 5 chiral multiplet carrying electric charge +1, and a single chiral multiplet P carrying electric charge -5. I also summarized their U1 R charges in this table, where the small q is a free parameter associated with this U1 gauge charges. However, because this is related to the U1 gauge charge, their dependence on the two-step partition function shouldn't appear. It's a non-physical thing. We also would like to introduce the Fi parameters and the theta angle with respect to this U1 gauge field, gauge group. And finally, we add to the theory the following superpotential, which is the T times the homogeneous polynomial degree 5 of this chiral multiplet. All right, so let's now compute these two-step partition functions using this exact formula I presented in the morning. So using that formula, this two-step partition function of this particular U1 gauge theory is given by this expression. This R represents the Fi parameter. So when this Fi, since we are interested in the geometric phase of this gauge theory, we will set Fi parameter R positive. Then we can rewrite this integral as a sum of the residue as a simple pole of this integrand Z5 to the nth power. And once you rewrite that expression in terms of, as a sum of the residue, you can easily expand that two-step partition function into the following form, where this parameter T can be understood as a nonlinear sigma model couplet constant, more or less the same as this complex by Fi parameters, with properly normalized, containing some instanton correction. Here, this first term is nothing but the classical term, classical contribution to this two-step partition function. Second term is a tautology correction to this two-step partition functions. And we can identify the various term in the second line as a non-tautology contribution, non-tautology correction to these two-step partition functions because it contains this e to the 2 pi tau or t vector, which is the instanton vectors. And from this expansion, particularly this number in front of this vector, we can read up the so-called Gromov-Witten invariant of this target space. And I just presented some of these numbers, the horrible numbers. And interestingly, these numbers exactly agrees with the Gromov-Witten invariant of this quintic threefold, which is already known in the literature from using the mirror symmetries. This is very nice, but furthermore, these people using this formula, they finally predicted some new result of the Gromov-Witten invariant of some Calabi-Yau manifold whose this mirror description is still unknown.
Sorry, where did you put in the information on the superpotential in that integration?
This R charges. So this R charge distribution, this assignment has to satisfy this condition.
You say that's the only way you take account of
yes. Yes, so this Calabi-Yau space is called the Glucosinegard determinant of Calabi-Yau manifold. Actually, I'm not sure whether I pronounced these two names properly, but never mind. So, and this Calabi-Yau manifold actually allows some non-abelian gauge theory descriptions, where the gauge group is U1 times U2, and this gauge theory is coupled to a bunch of chiral multiplets. And I just summarized their representation of this K2 gauge group in this table, and also U1 R charges of this matter field here. And I also introduced Fi parameters in the theta angle to each of these U1 vectors of the gauge group. And finally, we add to the theory the following superpotentials. And because of this form, some people call this a non-abelian gauge theory as a Pax model. So anyway, although we don't know this real description of this Calabi-Yau manifold, we can still compute the two-step partition function of this non-abelian gauge theory in 2 dimensions, which is given by these expressions. A little bit complicated, but following the procedure what I presented.
Sorry, so the Monte space is two-dimensional?
Yeah. Associated with the U1 vectors of these two gauge groups. Okay. And following the procedures, what I presented here for this quintic threefold example, just follow the procedures, then you can read up this Gromov-Witten invariant of this Calabi-Yau manifold, and this Morrison and company summarized their result in this table, a bunch of integers, sometimes remarkably long. And interestingly, this number, it is new result first, and they have shown that these numbers satisfy passive several mathematical consistency check too. So which makes us more convinced that somehow this formula, this two-step partition function, really compute the Gromov-Witten invariant or compute the exact Kähler potential in the Kähler modularized place of the Calabi-Yau manifold. So very nice, but at this point we need to ask the following questions and try to answer these questions. Why this formula works at the end. So this question was answered by Gomez and myself, and later on, these people, I don't know how to pronounce his name, Gorchkovich and Gomez and Komagaskis also provide third proof of this conjecture. So as a warm-up exercise, let me consider the simple and easy proof of this conjecture, which can be applicable only to the Landau-Ginzburg theories. So let's consider this Landau-Ginzburg theory that involves some twisted chiral multiplet, whose interaction can be described by these twisted superpotentials. And this Landau-Ginzburg theories describe a certain two-dimensional 2,2 superconformal field theory in the infrared. Then using these exact formulas, what I presented in the mornings, you can compute the exact two-step partition function of this Landau-Ginzburg theory, which is given by this simple ordinary integral, where the integrand depends on the twisted superpotential. And interestingly, it's been shown by Cecotti already in late 80s that these expressions is nothing but the integral representations for this quantity e to the minus k, where k is the Kähler potential on the moduli space of the corresponding and equal to superconformal field theories. So this is the end of this conjecture, at least for the Landau-Ginzburg theories.
Sorry, but I'm still not understanding how the integral is defined, because it seems to be.
It's a little formal. Yeah.
Wait, but if you can prove this, there must be some natural way to define it properly.
Yes, I mean, for instance, when this y, this imaginary part of this y is properly, how can I say, satisfied this, when this imaginary part of this y is compact, this integral type converges. You can show that. Yeah, we can discuss it. So in general cases, you are perfectly right. I mean, there are some issues about the convergence of these expressions. Okay, any other questions? All right, so let's now move on to the second proof of these conjectures for more generic cases beyond these Landau-Ginzburg theories. And this is the sketch of the proof. So here, we consider some supersymmetric theories on the squashed sphere rather than the round sphere. Here, the squashed sphere can be described by this embedding equation here. And to do that, we found that in order to define such a supersymmetric theory on the squashed two spheres, we actually need to turn on some background gauge field coupled to the UNR symmetric current, which is given by this expression. And then one can show that on this squash two sphere, we have two supercharges. And using that two supercharges, we can still compute the exact partition function of this two-dimensional theories on this squash two sphere. And we found that the squash two sphere partition function is actually independent of the squashing parameter B. In other words, we can deform this round two sphere to this squash two sphere without changing the partition function. And then let's now taking this, sorry for this illustration, but when then let's take this infinite squashing limit of this two sphere, so that we obtain some kind of infinitely stretched sausage-like geometries. In that limit, one can argue that the path integral of this supersymmetric theory on this sausage-like geometries as an inner product between the canonical ground state of given theories. Here, this canonical ground state corresponds to the identity operator inserted at the tip of this infinitely stretched cigar-like geometries via some operator state correspondence. So here, this operator state correspondence means that let's think about some operator inserted at this tip of this cigar-like geometries. That creates some state. That state will propagate along this infinitely long cylinder-like geometries, which will eventually project it down to some ground state. So, and then we have some state defined on this end of this boundary of the cigar. So that is the kind of pictorial way to understand this operator state correspondence. And this canonical ground state corresponds to the identity operator at the tip of the cigar. And due to this background gauge field, you have to turn on to define the supersymmetric theory on this geometry. One can show that this canonical ground state in the middle of these geometries is in the Raman sector rather than in the short sectors. And then it's been shown by Chicotti and Papa using TT star equation that this particular inner product between the canonical ground state actually compute this e to the minus k, where k is the Kähler potential on the Kähler moduli space of the given Calabi-Yau manifold. So using this result, we can compute the exact geometrical metric by taking the second derivative of it.
Sorry, is it obvious that the limit of the squashing two sphere is equal to the cigar geometry posed by the
Geometrically or some other
yes.
thing concerned here? What kind of concern?
I'm not really sure that it's the same as the cigar geometry and
the theory defined in the cigar is a little different, right? There's, in TT star construction, they define this topological A model on the cigars and anti-topological A model here. We have some physical theories, right? But still, one can say that any state created by this operator insertion here will be projected down some ground state at the end. That's for sure, right? And the question is whether or not this ground state corresponds to the canonical ground state, what Chicotti Papa said. Well, there is some discussion. It's a little subtle issues, but what one can show that, how can I say? So, in the case of the TT star case, there is an unbroken axial UNR symmetries, which will distinguish different type of ground state here. And this canonical ground state carries zero axial UNR charges. But here, the one slight, might be potentially problem is this on this two sphere, axial UNR symmetries now is broken. That's a problem. But in other way, so what one can show that, so that implies that when you act this U1 axial R symmetry rotation on this supersymmetric theory on the two sphere, you can generate one parameter family of this supersymmetric theory on two spheres, which are related by this U1 axial R rotations, right? So we have one parameter different family, one parameter family of the theories on two spheres. And when you compute two sphere partition function of this theory, you always get the same answer, which means, at least in the language of the two sphere partition functions, somehow this axial ionar symmetry is restored, at least for this observable only. So then we can use this argument. There are some axial ionar symmetries. So this ground state must carry 0 axial ionar symmetries. You understand what I'm trying to say? Yeah.
May I attempt a different proof? Naively, I would take 2 derivatives on a partition function and relate the sphere 2-point function. If I naively do that, I would not quite get the right homological metric because I'll get partial k, partial bar k terms. But that's presumed to do some contact terms when you integrate 2-point function.
Yeah, that's the proof of. Okay, that's the last part I want to make a comment actually.
Right.
So, a few months ago, there was a paper by Gomez and Komagaski and other persons who used that paper to provide the third proof of this conjecture. Yeah, they used the conformal order identity under this contact condition. Any other questions? All right, so this is the end of this proof of this conjecture. All right. So let me now move on to different topics. So from now, I will discuss about some issues about the Ramon-Ramon charges, which gamma classes, and so on and so forth. So what is that? So in 2013, string conference in 2013, there was a very nice talk by Dave Morrison, and in that, who was talking about this recent development in computing the Gromov-Witten invariant from the two-sphere partition function, what we just discussed. And during the talk, he mentioned, he made a very interesting comment on the D-branes charges, which I put here. So basically, he said there are several mathematicians, including Konchevich, who proposed a modification of the conventional form of the D-branes charge from this to this. I will explain what this letter actually means later, but they proposed a new expression of the D-branes charges, but this expression was very confusing to me for many reasons. And that was the reason why I wanted to study this Hemisphere partition function and RP2 partition function carefully to understand what this issue really means and how to resolve the puzzle I had at that time.
When you say in favor of this, what does that actually mean? Is there some property that you want to obey that's not affected by the old expression?
Sorry?
Before that was just a map from K0 to the homology. When you want to modify, what's the goal? What is the property that the old map that you're not satisfied with?
Satisfied what? It doesn't satisfy what? Sorry?
No. Well, why are you not happy with the old map from K3 to?
Why mathematicians propose this new expression? This is your question.
Yeah.
Because of some, they derive this result from the mirror symmetry point of view. I will come to.
Wait. This is a map that you can define as a map from K3 to the homology ring. So, when you say derive the map, you're demanding some property on the map. What is the property that you want this map to have? That old version does not apply.
I don't know whether I understand you.
No, I don't understand the purpose of, or what is the property that you want to demand for this map from K3 to the homology ring? It must be somehow that you.
The only way I understand this is there is a way to determine this Ramon-Ramon charge of D-brane from the anomaly inflow mechanism. Is that will determine the conventional form of the D-brane charge, what I'm happy with. But somehow the mathematician, for some reason, modified the expression. The D-brane charge expression, which I will discuss in a second. So I'm not happy with that. That was the modification for it.
Wait, is this a modification of definition or
modification of the expressions? A principle.
Well, I don't understand what is the question that this is answered to.
I think I don't understand your question well, but maybe from next slide maybe you can ask the question again. Yeah. All right. So in order to understand these issues and the different charges more clearly, let me go through some history a little bit. So let me first start with this minimum coupling of the D-brane to the bulk Ramon-Ramon gauge field, which is given by these sections. This coupling is known as the Westermüller coupling or Chern-Simons coupling of this D-brane. where M is the wall volume of this D-brane, and C is the Raman-Raman gauge field in the bulk, and Q is the Raman-Raman charge of D-brane, what we would like to determine. Right? And as some of you may know, some of you know very well, there's a long history to find the correct form of this Raman-Raman charge. And this anomaly inflow mechanism has been very useful to highly and strongly constrain the possible form of this D-brane charge. So let me first briefly review the basic idea of this anomaly inflow mechanism. So for simplicity, let me consider the stack of DP branes. Everybody knows that the low energy effective theory living on the stack of DP brane is given by maximally supersymmetric Yau theory in P+1 dimension. And this gauge theory has SO9 minus P R symmetry, which is a global symmetry, where 9 minus P is the dimension of the transverse space to these D-branes. But in some cases, like a D5 or D7 branes, one can show that this R symmetry is anomalous. But that's perfectly fine within the context of the quantum field theory, because this is just an anomaly of the global symmetry, Tooth anomaly. However, as soon as you couple this theory to the gravities, this SO9 minus PR symmetry become a part of the diffusion fusion group, which is the local symmetries. So we have a local symmetry anomaly, which make the theory ill-defined. So this is a serious problem. However, we believe that the string theory has to be consistent theory all the time. So, which implies that the action describing this whole system, which consists of this following three terms, the bulk, type 2A or B, a superstring action or supergravity action, D-brane action, and the minimum coupling of the D-brane to the bulk Raman-Raman gauge field. This whole action has to be invariant under this SO9 minus P rotation. And that implies that the anomalous term, which arises from this D-brane actions, the variation of this D-brane actions, has to be cancelled by this variation of this best-terminal coupling here. And this requirement provides a strong condition that this Raman-Raman charge should satisfy. So this is the basic idea of this anomaly inflow mechanisms, how this anomaly inflow mechanism can constrain the possible form of this Raman-Raman charge. And this, actually, people study this anomaly inflow mechanism in many different settings, such as D-brane on top of each other, or intersecting D-branes, and so on and so forth. And there was a lots of papers along these directions. I just summarized some important references here. But this topic was studied by really many people. It's actually a very interesting history because these people first proposed some expression for these D-brane charges. But it turns out that their expression is incorrect. They missed something very important factors. So these two people, Cheng and Yi, proposed another expression for these D-brane charges, taking into account these important factors. But later on, this expression turns out to be incorrect again. So these people proposed another expression for this D-brane charge, and so on and so forth. And at the end, the D-brane charge inferred by, we determined this D-brane charge inferred by this anomaly inflow by these expressions. So this is the Chern character of this world volume field strength in the D-branes. B is the NSNS two-form gauge field in the bulk. And we have an additional vector, which is the square root of the A of genus of tangent bundle over A of genus of normal bundle, where A of genus is given by this expression. Well, here we just formally expand these expressions like this, and then insert this coverage 2 from here. And because of these additional vectors, sometimes this additional vector sometimes induce a lower dimensional D-brane charge, which is known as the geometric Witten effect. For instance, it is well known that the D5 brane wrapping on some K3 surface can induce -1 D1 brane charges because of this vector. Similarly, we can also determine the Raman-Raman charge of the orientable plane using this anomaly inflow mechanism, and the expression is given by this one. So this is a very important vector for the test for cancellation. And plus minus sign will distinguish different type of orientable plane, or plus and or minus. And we also have this expression which involves some different characteristic class called the Hilsbrook class given by these expressions. And furthermore, by computing this disk amplitude with the raw